Okay, I think we can start. Good afternoon. First of all, I would like to thank all the speakers of the morning session for their nice and interesting talks. And now we shall start the first afternoon session. I would like to invite my collaborator, colleague, and friend for several years, Lucio Crivegliari, from Instituto de Astrofísica de Canarias, from Spain, and also from the Astronomical Observatory of Trieste in Italy. His research focuses are on radiative transfer and stellar atmosphere theory, and I would like to point out that he's the author of 3 very important books on spectral line formation, on stellar atmosphere modeling, and radiative transfer in stellar and planetary atmospheres. So, Lucio, please, you can start your talk.
Thank you, Olga, for your kind presentation. Good afternoon to everybody. My only regret is not to be in Belgrade today to enjoy once more your warm.
We regret too.
Like 3 years ago. When I received your invitation to deliver an invited talk, I was really flattered. Later, my concern was about its content. In lack of new appealing results of my current research project, eventually I had rather to present a retrospective that looked back at the numerical methods and algorithms to whose development I contributed, well, along 3 decades, and Olga also was an important part of it. Of course, I am not going to deliver a lecture to an audience of practitioners. The stellar atmosphere problem, which is at the center of my title. The stellar atmosphere problem was defined by Larry Auer as the solution of the RT equation subject to constraints. But I will go beyond this classical definition and say that the stellar atmosphere problem is the consistent solution of all the equations that define the structure of the given stellar atmosphere under specific physical assumption. And in the following, I will enter into the definition of what I define the stellar atmosphere physical problem. However, before all else, I wish to pay a due tribute and remind the starters of the line of thought underlying the methods and algorithm I am going to present to you today. Firstly, Jean-Claude Pecker. Jean-Claude was one of the fathers of modern French astrophysics, a great scientist, a true-born gentleman, and also a fine painter. Some of the background of some of my slides are drawn from this booklet, Plage d'Encre, that are what colors presented by Jean-Claude many years ago at an exhibition. And then Françoise Pradry, I had the good sort to work with her at the Meudon Observatory in the first half of the 80s of last century, and then at the Institut d'Astrophysique at Paris, where I was introduced by Françoise to my now great friend and mentor, Edoardo Simoneau. Edoardo is the father of all the method and algorithm that later myself and Olga and a few other co-workers developed. I am going to speak about, firstly, the methodological framework. Then, as promised, I will define the stellar atmosphere physical problem. to introduce then the novel methods and algorithms, a global iterative sequential approach, and the iteration factor methods. Finally, I will briefly speak about future perspective of a research work I started a couple of years ago with some Italian colleagues. The algorithmic representation of physical system. Forgive me to introduce a zest of epistemology. By means of our senses, we perceive the outer world. What then is the underlying reality is a matter of philosophy. Let me just say that I believe that the task of physics is to give a representation of the phenomenological world, what we see, what we observe, what we measure. In this, I am a follower of Galileo's legacy, and in particular, as you will see, I am a follower of the operativism, an epistemology current introduced by Percy Bridgman. Bridgman maybe is not well known nowadays, but he was Nobel Prize in 1947 for his work on thermodynamics, and introduced this new line of approach to the physical representation of the physical world in terms of operations. A basic reference, my seminal paper in this field can be found in this book, The Role of Mathematics in Physical Science. The aim is to get an effective operative description of physical systems. And the basic concept in the representation of the structure of the physical systems are individual components. This is an important point. We individuate components and we identify and quantify these individual components by means of physical variable. In a way, we can set a one-to-one correspondence between the physical variables and the physical quantities. Then, another important ingredient is the state of the system, and we describe the state by means of the value of the fundamental variables, all those and no less than those that are enough to describe. And eventually, what is possibly the most important item, we can see a hierarchy of interaction, a hierarchy, this is a key word, that shapes the structure of the physical system. Ideally, we can dissect a physical system into a set of simpler interacting parts, and these allow us to describe the global behavior of the system in terms of the law that govern each one of its elementary components. This ideal process leads eventually to a model, as this model is defined operationally, I mean in the spirit of Bridgman, through a series of either physical measurements operation or mathematical abstraction. And this is a model of our perception of the physical world. Modeling, needless to say, is an unparalleled tool for a scientific inquirer because, thanks to its analytical nature, it can be easily translated into a mathematical model. And though we reach at this flow chart, the fourth step which allow us to pass from the physical world that we observe and measure to a continuous model. From the continuous model, by means of mathematical abstraction, we get a discrete model. We pass to a discrete model, and from this discrete model, we are in a position to design a numerical algorithm. The physical world has a direct influence both on the discrete model and the numerical algorithm. On the other hand, we can consider the numerical algorithm as a representation of the physical world. It is essential at this stage to discover the optimum algorithm. And for this, let me quote a sentence by Henri Poincaré. Physics not just give us the opportunity to solve problems. Physics also let us foresee the solution. This is one tenet at the basis of all our search for optimum algorithm, as you will see in the following. Modeling implies both the study of the structure on the left side of the slide and the design of the algorithm, which of course comes from the stellar atmosphere problem. Though we have the physics in terms of law of conservation, transport processes, initial and boundary conditions that govern and shape the structure. On the other hand, the stellar atmosphere problem is a non-local and non-linear problem, and that reflects into the algorithm. The two ways determine the model. The structure, I will see once more, is described by the value point by point of the fundamental value, the fundamental variables. The values of the variables are determined by the relation among the variables themselves, the constraint imposed by the external condition, and the internal energy of the system. It's a moment now to try to define what I consider the stellar atmosphere physical system. It is defined by its fundamental equation. What normally are called the constitutive equation, that is the equation of mass conservation and the equation of motion. The macroscopic equation of state for matter, the constraint of energy conservation, both for matter and the radiation field, transport equation that describe how energy is carried on either by radiative or convective transport, and a microscopical description of matter in terms of the atomic occupation numbers. The equation of state, which is important, I will immediately later enter into detail. You will see the equation of state link the mechanical with the thermodynamic state of the system. On the other hand, the microscopic state of matter is described, as I have said, by the atomic occupation number. If we can assume local thermodynamical equilibrium, these numbers are function just of the thermodynamic variable following Boltzmann and Saha statistical law. On the contrary, when the condition of local thermodynamical equilibrium is not fulfilled, also radiation field enter into the determination of the atomic occupation numbers, and we must solve the system of equation of the statistical equilibrium. Then we can define, in the usual way, macroscopic transport coefficient for emission and attenuation of radiation, and these macroscopic coefficients include all the microscopic information on the radiative transfer, on the absorption and emission processes. I just mentioned that in our approach to the problem, we always consider a semi-classical picture, and radiative processes are treated in terms of Einstein phenomenological theory of 1917. The macroscopic transport coefficients determine univocally the radiative transfer specific, that is, monochromatic equation. The essential difficulty is that all the physical variables interact through the whole atmosphere. That is, the problem is non-linear. And the local variation of one of the variables can have an important effect on the local properties at great distance. That is a non-local problem. Well, in principle, by means of the proper linearization technique, it might be possible to convert the original system of equation into an equivalent system of linear algebraic equation. This is represented by a matrix, and each element of this matrix, the metric of the mathematical system, reproduce for the nature and collocation of its element, reproduce the structure of the initial physical model. In other words, and in my line of thought, this matrix can be seen as one possible algorithmic representation of the stellar atmosphere physical system. All that look nice, but there is a severe problem. Because it is well known that in the practice, the numerical inversion of large or ill-conditioned matrices is a nasty problem. So how to get rid of this? Before going to the solution we propose, let me quote this seminal paper by von Neumann and Goldstein. Take note that it is a seminal paper published in 1947 at the beginning of computational physics, but their tenet is still valid. Exact arithmetic, by exact arithmetic they mean transcendental operations. When exact arithmetic is replaced by approximate arithmetic, that is, elementary operations handled by a computer, no computing machine, neither at that pioneer time nor nowadays, can perform faultlessly all the operation, because the number of digits available is always finite. Then, and on the way to get rid of the fundamental problem, let me remind that the complete linearization technique rests on the assumption, as given explicitly by Michalas in his book Stellar Atmosphere, no variable is more fundamental than any other, for they all interact. And this is an equality treatment that I compute because different processes are characterized by very different scale, and the strength of the coupling between the different problems may vary considerably case by case. Though, what we introduce is an iterative sequence procedure. We group into elementary blocks atomic self-consistent problems. Atomic in the sense that the physical information inside the block cannot be further reduced. The block contains the physical information on the one hand, the algorithm on the other. We have an input, and the input are the values of the variables external to the block. We solve the physical problem inside to get as an output the values of the internal variable that are the solution of the block. This is the essence of the mean. So, to give you an idea, let us consider a simplified case of an atmosphere under both hydrostatic and radiative equilibrium. We have a mechanical block, I have already anticipated, that include the conservation of mass and momentum linked with the macroscopic equation of state. We have two equations for three variables, though we need one more. And this is the central idea. We start with a guess of the value of the temperature. The temperature is the protagonist variable. We enter with a guess of the temperature. We solve the mechanical block, and we get out with the temperature and velocity, density, pressure. With this ingredient, we can give the microscopical description of matter. We determine the Planck function, the macroscopic transport coefficient, and enter in the energy blocks, where we solve sequentially the radiative transfer equation to get the values of the specific intensities that characterize the radiation field, and we enter into the energy conservation equation. This is a checkpoint. Is the conservation of energy satisfied? The initial guess of the temperature was correct. Fine. But in general, this won't be the case. Thus, we use the energy conservation equation as the corrector of the temperature to obtain a new temperature, and we go at the top and repeat. This is the natural sequence. I go rapid through this and call your attention on the energy block. Here we have a sequential solution: temperature, Planck function, macroscopic transport coefficient. We solve in sequence the radiative transfer and go to the conservation of energy. But this scheme is the well-known from the practitioner in the field of radiative transfer and stellar atmosphere, the well-known lambda iteration, which in the practice doesn't work. So a first step was to reconsider the radiative equation. All the energy subtracted from the radiation field is given back by the emission process, in this case under consideration, given by the Planck function, LTE hypothesis. This is a definition of the quantity JA, which will be used in the following step. We can linearize the Planck function around a temperature T0, and then we can derive expression for JA and the difference T, the actual temperature, minus T0, the current temperature around which we have linearized the Planck function. In this way, we can write the monochromatic Planck function in terms of a non-function of the current temperature another known function of the same variables, and the term JA that considers the energy subtracted from the radiation field. And in this sense, we can write for each frequency the source function, and this source function, this is the important point, includes now the radiative equilibrium constraint. So what happened? We go to this new scheme where the solution of the radiative transfer equation and the energy conservation are solved simultaneously. It is an important step forward, but there is a problem. The coupling between the two equations is brought about by this term that include all the monochromatic solution of the radiative transfer equation. We define this coupling as strong, and its solution by means of an iterative algorithm is very long and doesn't work with the quality we require to the method. And so, Edoardo Simoneau, in the 80s of last century, introduced the iteration factor method. These are the two basic references, Old Matter, 1988 and 1991, but the work is still alive. The essential of the method. AP is the standard, the usual definition of a mean absorption coefficient in terms of the Planck function, the so-called Planck mean. Also, another standard mean of the absorption coefficient is the radiation mean, defined in this way. And what is new, the definition of the iteration factor alpha as the ratio of the two mean, which is the essential characteristic of such a quantity. This is the ratio of two homogeneous quantities. Though along an iterative procedure, when we start with values which are far apart from the correct solution, the ratio between the two homogeneous quantities in a way can reduce the spurious information carried on along the step of iteration. If we take into account the constraint of radiative equilibrium, the previous equation can be written in the form AP times B equal AJ times J. B and J are the integral over frequency of the monochromatic Planck function and mean radiation field. So, we can express the Planck function, which is a function of the temperature, in terms of the iteration factor alpha and J computed from the solution of the radiative transfer equation. And immediately we can use this formula as a corrector for the temperature and obtain the new temperature in terms of the iteration factor alpha, which has the essential property of being quasi-invariant along the step of iteration, and the integral of the radiation field, as I said, computed from the solution of the radiative transfer equation. So, this is the new scheme, sequential solution, where we enter with the external value. We solve the radiative transfer equation from the value of the radiation field we determine its moments J, H, and K, and compute proper iteration factor. After that, we go back to the simultaneous solution of the radiative transfer equation and the energy conservation, but rewritten in a new form using the iteration factor. And in this way, the coupling now is weak in the sense that it is a matter of experience. Now the number of iterations required is dramatically reduced. I hope that in this necessary swift presentation I have given you a flavor of the method and just mention the important work developed by Olga and her co-worker at the Berger Faculty of Mathematics, the seminal paper with Edoardo, and a recent work with Olga Kuzmanowska-Barandowska, starting from the academic two-level atomic line problem to a multi-level atom line transfer. Then another important contribution of Olga, together with Edoardo, was what we call the forward and back implicit lambda iteration. It is not time to give you details about the method. Let me just show you two diagrams and consider the number of iterations with standard method and the dramatic fall in number of iterations with the forward and back implicit lambda iteration. This is for the academic case of a two-level atom, and this is a more recent result applied to multi-level line transfer. What I wish to stress as a conclusion and to prove my initial statement, all these results have been obtained by taking into account the physics of the problem. And the ultimate tenet again, the physics of the problem dictate the optimum algorithm. I wish to mention also the work by Olga for application to radiative transfer in two dimensions with Ivan Milic. And I will quote the book recently appeared, the book of the Winter School held in 2017 at the Istituto de Astrofisica de Canarias, and the chapter 3 by Olga is a very nice and exhaustive result of numerical methods in radiative transfer. I will finish very quickly by mentioning my research work in progress. 3 years ago, I was contacted by my colleague and new friends Sergio Cristallo and Luciano Pierasanti at the Osservatorio Astronomico di Teramo, and also member of the Sezione di Perugia of the Italian National Institute for Nuclear Physics. The aim is to study AGB stars and their circumstellar envelopes. For them, the central point is to model both the physics and the chemist in order to study dust grain formation. But from my point of view, and the contribution they asked me, is to solve a radiative transfer problem in dusty envelopes, because we have the dust concentration and growth in a region with strong driven wind. And we have also radial pulsation and all these of difficulties, and all that require a proper treatment of radiative transfer. And though the idea is to implement this novel algorithm, quite old, by passing an implicit integral method to solve selected radiative problem. These 4 papers where this new implicit integral method is described in full details. We are going on in this line with Sergio and Luciano, and recently we succeed to implement into the code a radiative transfer in 3 dimensions. I will stop here. I hope that my presentation has not been too much messy, and ready to answer your question, criticism, doubts. Thank you
very much
for your attention.
Thank you very much, Lucio, for a nice review. We have 4 minutes for questions and answers. Do we have some questions? If not, maybe I could ask you something. Is this the range? In fact, if we could say that the range of interactions in fact determines the coupling. Is it strong or weak? And the way how to solve the problem, in fact. I mean, do all the transport processes imply strong coupling? Is it the non-local nature of the problem or necessarily the non-linear one?
Both of them. Non-local, but
and non-linear.
above
yes.
all the non-linear.
Yes. So this is not only the range, I mean the long range interactions that lead to the strong coupling, but it is necessary that
yes,
we have non-linearity in our problem.
Strong coupling is brought about by the non-linearity, essentially. Yes. The distinction between weak and strong indeed is quite loosey, and it is determined a posteriori by the way we can solve it. What I tried was to compare the natural sequential procedure, the intermediate step, where the radiative transfer equation and the energy conservation were coupled together. And in this case, experience shows that the convergence is improved because, as a matter of fact, lambda iteration does not converge at all, but very slowly. And the ultimate solution was to soften the coupling by introducing our iteration factor. Yeah. Once more, it is a posteriori evidence that this technique, this new iterative scheme, works better and quickly, and we have softened the coupling.
Yes. Thank you very much, Lucio. Your last slide was about the low mass stars and the winds of low mass stars, yes?
Yes.
You will work on them, because Jiří Kubat, our next speaker, will talk us about winds of massive stars.
Yes, this was a special reason to present this funny picture by Sergio, which gives a flavor to the problem. And of course, is the problem that Jiří will address.
Yes. Okay. Thank you very much. Thank you very much for a nice review. And now we have the next speaker.
I have to
stop. Yes, thank you. Our next speaker.
Okay?
Yes.
Okay.
is also our colleague and friend for many years, Jiří Kubat from the Astronomical Institute of Academy of Sciences of the Czech Republic from Ondřejov. His research fields are also on radiative transfer, theory of stellar atmospheres, non-LTE, physics, dynamics of stellar winds. He's the author of the computer code for calculating non-LTE model stellar atmospheres in planar and spherical geometry. And he was a deputy director of the Astronomical Institute and the head of stellar department. And I'm very glad that he is now with us and that he will give us a talk about the winds of massive stars. So you can share your presentation, Jirka. Okay, thank you. Jirka, you have to unmute your microphone. Did you? I can't hear you. So please unmute. Yes.
Now
yes.
It's good?
Okay, it's okay.
Okay.
Thank
Okay. So I apologize for the technical problem, which was caused by improper contact in my laptop. So it's a thank for inviting me to the conference, which is unfortunately only virtual. But nevertheless, we shall do our best. So I will talk about the mass loss rates in massive stars. And the massive stars, what I mean, are usually the hot stars, not all kinds of massive stars. So first I will talk how we determine basic parameters, wind properties. It means terminal velocity and mass loss rate. And then I will stop at several types, how we can model the stellar winds. So massive stars are very important in nature, like every star. But they are very, their properties are they are hot, luminous, and massive, up to tens of solar masses. They live very shortly, and usually end as supernova explosion. And they are also very rare, and they form only a small fraction of stellar population. But they are important because they can be seen at large distances, and they are very important for the environment. They enrich the interstellar medium exactly by the explosions of supernovae, and their evolution is quite a tricky task. And all the evolutionary analysis and calculations needs good information about stellar winds and mass loss rates. So let me concentrate on the mass loss. Mass loss, the properties of mass loss are the mass loss lowers the stellar mass, of course. Stars can lose up to 10 to minus 6 or even more solar masses per year. And this mass loss rate is a very important parameter in all stellar evolution codes. Main task of quantitative spectroscopy of massive stars is knowing stellar mass, radius, and so on, mainly determination of terminal wind velocity and the mass loss rate. So how we can determine these quantities? First, the simpler case, this is a terminal velocity determination. This quantity can be measured directly from the spectrum, where the distance from the line center to the blue end of the line determines the terminal velocity. It can be measured if you have a nice with a good nice p signet profile of a line, so it can be measured with a quite good accuracy. On the other hand, the mass loss rate, we cannot measure. We cannot come to the star and count the mass. So we rely on some comparison of model prediction with observations. And if we find that the spectrum fits, so we call the result the observed mass loss rate. But in fact, we compared just the spectrum. And because the problem is quite complicated, many approximations are used. So the standard assumption is spherically symmetric wind or atmosphere, and with homogeneous spherical shells. So it excludes many properties of the wind. The wind is stationary, doesn't change with time, and one of the old approximations is the so-called core halo approximation, that nothing from the wind influences the photosphere, which we succeeded to relax a bit, but still it's a very often used approximation. So, and how we can model the wind? There are several ways how to attack this problem. First, let us assume that we know the stellar mass, radius, luminosity, and the chemical composition or the metallicity. And the goal is to compare the observations with theoretical calculations. And what we want to determine for the mass loss determination, we want to determine the mass loss rate. And for this, we need to know the density and velocity structure of the wind. So, and there are several options how to come to this problem. Some parts are given, some quantities are given, and some are determined. We are interested in the radiation field, which can be compared with observations. So in the simplest case is that we assume that we know temperature, population numbers, density, and velocity, and we determine the emergent radiation with the oversimplified assumption of no opacity. It's in fact the formal solution of the transfer equation, but with this assumption, it gives very fast results, and it's often used for optically thin media, for example, for radio determination of mass loss rates, but it's very simple, but it gives very fast results, not too much accurate. Much better is that we solve the radiative transfer equation for given opacity and emissivity. So the formal solution of radiative transfer equation, and usually this approach, not necessarily, but usually assumes local thermodynamic equilibrium. Even better option is to solve the so-called non-LTE line formation problem. It means that we do not assume that we know the occupation numbers, we determine them, but we assume that we know the structure of the atmosphere, temperature, density, and velocity. So, and in this case, we have to solve the radiative transfer equation together with the statistical equilibrium equations. So this is a typical non-LTE line formation problem. But in the analysis of stellar winds, a different approach is used, because here we have to assume the density and velocity structure, which we have to determine by other means, somehow using some hydrodynamical modeling. But to avoid this complicated hydrodynamical modeling and have some kind of quasi-consistent solution, we assume that the velocity structure is given by the so-called beta velocity law. So we assume this dependence, and for this given beta velocity law, we determine the density using continuity equation, and we solve the non-LTE line formation problem like in the preceding case. In this case, the mass loss rate is given. And this, I emphasize this as one of the selected models I will talk later about. This is usually called as non-LTE wind model. So the main results of non-LTE wind modeling are based on this approach to the wind modeling. Another option of this wind modeling is that we do not assume temperature as given, but we add the equation of some thermal balance of radiative equilibrium to the set of equations being solved. But still we have to assume somehow the velocity dependence on radius, which can be avoided if we try to calculate such global models of stellar winds where we solve all of the equations: continuity, equation of motion, radiativity transfer equation, kinetic equilibrium equations, and also some energy equation, radiative equilibrium. And this is full radiation hydrodynamics modeling. It is the most complicated and time-consuming option, but gradually we are coming to the situation that it is possible. And this gives consistent values of mass loss rates and terminal velocities. And finally, now we go a bit back. It's called hydrodynamic wind models, I call this. And this type of modeling assumes, takes given radiation field and also the occupation numbers, and consistently solve the continuity equation of motion and energy equation in the stellar wind. So this we call the hydrodynamic wind model, but this modeling doesn't give us the emergent radiation because we assumed radiation field, but it gives the structure. And now with some combination of modeling, we come to some solution. So let me stop now about the talk, say a bit more about the highlighted models. So first, the last one, hydrodynamic wind modeling. So what does it mean? We solve the continuity equation, equation of motion, and energy equation, which is quite long and I didn't list it here. And they are stationary. And as a result, we obtain solution of this type, which is a typical figure how the solar wind looks like, but for the stellar wind, it is very similar. And the solution is usually used as this line coming through the so-called critical point to the infinity. And the value at the end of the wind is the terminal wind velocity. So this is a solution of hydrodynamic wind models. And what is the main constituent of this driving of the wind is radiation force, which accelerates the wind. It is just the integral of this term along all frequencies and directions. But this equation is quite complicated. So people came with approximations, which is called the CAK approximation, Castor-Abbott-Klein. But for this approximation, you need the radiation field is, the radiation force is approximated by these three parameters. And then the radiation acceleration, which is necessary for the calculation solution of the wind, is solved using this simplified equation. However, if we want to solve this problem, these type of models do not offer usually an emergent spectrum. They consistently calculate hydrodynamic equations, and as a result, they solve the density and velocity field, which gives the terminal wind velocity and the mass loss rate. And this value of mass loss rate is called the predicted mass loss rate. So people usually refer to this value coming from hydrodynamic models as predicted mass loss rate. On the other hand, the non-LTE wind models, they do not solve the hydrodynamics, but they assume the beta velocity law, which differs slightly from the hydrodynamic solution, and solve in detail radiative transfer and the statistical equilibrium equations, and sometimes also some temperature, some energy equilibrium equation, radiative equilibrium or thermal balance. Typical representatives, I think the only three, are the codes Power from Potsdam, Fast Wind from Munich, from Joachim Puls, and CMF Gen from Pittsburgh, John Hillier. So, and this type of modeling takes assumed velocity profile and mass loss rate. Then the full non-LTE line formation problem is solved and some spectrum is predicted. And such mass loss rate is usually called, and then this result is compared with observation, and such mass loss rate is called the observed mass loss rate. So this is how people are working now, and usually if the predicted and observed mass loss rate match, we are happy and we have the solution. But so this is schematical picture of this. So from observations, we come to we measure the terminal velocity, and using non-LTE event modeling, we determine the mass loss rate, and we finally compare it with some basic stellar parameters. And from these basic stellar parameters, we solve the hydrodynamic event model, and again, we determine the mass loss rate. And if we match, so this is the solution. Here, the velocity field is assumed, and here, the radiation field is assumed. So this is efficient, but not ideal case. So to move a bit forward, we come to global non-LTE event models. And with this modeling, we solve the continuity equation, equation of motion and energy equation, like the hydrodynamic part, and the radiative transfer equation plus kinetic equilibrium equations as the radiation transfer part. And from these quantities, we, for given stellar parameters, properties of the star, we obtain consistently the mass loss rate and terminal velocity. Some common assumptions are released, so it means that the line radiation force is not taken parametric anymore, but from non-LTE occupation numbers. And the photosphere is also included to the wind, so the core halo approximation is also released. So what we solve is the detailed description of the line force. I repeat here this equation, and we solve this equation together with the occupation numbers. And for the radiation field, comes to the equations of the kinetic equilibrium, we either use a Sobolev radiation transfer, which is a bit faster, or the moving frame radiation transfer, which is a bit slower but much more exact. So when the photosphere is part of the model starts at large optical depths, and there is a smooth transition from the photosphere to the wind. In the approximation, in the so-called core halo approximation, there is no influence of the wind on the photosphere. It's some model block. And the photospheric radiation is taken like a lower boundary condition for wind. And of course, there is always a problem of the transfer from photosphere to wind. It can, with difficulties, become smooth. Many times it's not smooth. So what are the properties of global wind models? Arbitrary chemical composition, no need to use force multipliers. And they also allow to check if the wind is present, because not all stars must have the wind. And the transition from photosphere to wind is smooth. Here we did some calculations with some results. And just to summarize, there are some model tests for metallicity of Milky Way, Large Magellanic Cloud and Small Magellanic Clouds. And in all cases, we arrived at mass loss rates which are lower than the ones which are considered like standard ones, which are calculated using a formula by Yorick Wink. Also, the velocity law is improved. It's not the beta velocity law like it is described here. Beta velocity law is a full line, and the correct profile is slightly different, but this slight difference makes quite big results in emergent spectrum. So maybe I can stop also here. Another property which is very important for modeling is clumping. So it means that the wind is not smooth as is assumed, but that it forms some kinds of structures which are called clumps. And of course, these objects are spherical, are not spherically symmetric, and one should use 3D modeling for this. But for 1D modeling, it's quite complicated, quite tricky, but it's to some approximation, it's feasible. So if we assume that the clumps are optically thin, so it means that the optical thickness of the clumps do not change. So that the mean free path is the same or comparable. So then the clumping can be described by some clumping factor, and 1D non-LTE event models with the clumping factors with included clumping yield lower mass loss rate. Much better treatment is the allowance that the clumps may become optically thick. We call this macro clumping. But in the 1D modeling, it's very tricky or almost impossible. So we have to switch to 3D modeling, which we some time ago did. And there is some comparison of selected line profile calculations where the black line is calculated with clumping and the red line is calculated without clumping. So, but this dotted line, this black line, was calculated using 3D Monte Carlo radiation transfer in selected spectral lines. So it's so computationally demanding that modeling was still not possible. Full hydro radiated transfer modeling of all spectrum is still beyond the possibilities. So, and there is some work which is in progress because we do not want to stay at the moment, we want to do some progress. So 3-dimensional non-LTE wind code, we are, or our PhD student is developing, and it uses Monte Carlo radiative transfer and kind of approach to non-LTE using Monte Carlo, which is called macroatom approach, developed by Leon Lucy. So this is a complete new philosophy, and this work is in slow progress. So to summarize, how to determine the mass loss rates? Using non-LTE wind models with a given beta velocity law, it's one option. And these values of the so-called observed mass loss rate are verified by hydrodynamic wind models. We call them predicted models. And this standard option should be replaced by radiation hydrodynamic non-LTE wind models. And the way to do this is to use global wind models which improve the mass system analysis and offer a more reliable tool for modeling atmospheres and winds. And back to this, to the scheme which I drew here. So this is a current way of determination of mass loss rate that we come to that we observe the mass loss rate and predict mass loss rate, and if they match, so this is we call it success. But the next step should be that we directly determine from modeling the mass loss rate using more equations. So thank you very much.
Thank you very much, Jirka. Thank you very much, really, for a very nice talk. We have enough time for questions. We have 5 minutes. I forgot to say that also, if you don't have time for questions, you can use chat. So in chat, you can ask some questions. But now you have the possibility to ask directly the author of this nice talk.
I know it's a bit difficult to ask. I also have troubles to ask with online discussion.
Yes, because you didn't unmute yourself. Huh?
Yeah.
Oh, I'm sorry.
Okay.
You can ask now.
No,
because
no.
If there is nobody, I don't know, please. Do we have some questions? I don't see hands raised. If not, I would like to ask you something. You said that you compare your computed spectra with the observations. And I'm interested in what are the lines you use for comparison? Are they usually UV or maybe infrared, in infrared lines? Unmute, please. I can't hear you. Yes. It's okay.
Sorry.
Okay.
Sorry. It's usually we use UV lines, but if we compare the results of the non-LTE wind modeling codes like this POVAR CMFGen, so they have really very sophisticated output. So this we do not have yet. So we compare some lines, but we still need to do some work on detailed comparison of line by line, because we are concentrated on the most important lines for modeling, which is not always exactly the same like for observations, because there are some lines which do not affect the atmosphere, but you can observe them. So, and these lines usually we do not include in detail. So there are still some practical steps, but the UV lines are most important.
Yes. Yes, because turbulence can make the definition of ultraviolet edge difficult. So sometimes it is maybe better to use infrared lines, but that's because, that's why I ask you that. Okay. So if there is no other questions, oh, there is Istvan Vince. Please let Istvan Vince to ask. Istvan, please unmute yourself.
I try.
Okay.
It's okay?
Yes.
Yeah.
Tell me, it must be observed only the resonance lines for determination of the terminal velocity, or it is...
For the terminal velocity, I think we need quite strong lines that have the P-Cygni profile with well-defined edge. It's the best.
Yeah, okay.
And for the mass loss rate, there are many lines which are sensitive, and usually if we compare the ultraviolet part, visual part, or the infrared RGB observations, they need to give the same result, which sounds trivial, but sometimes they do not.
And what do you think about if the star, for instance, in a close binaries has a optically thick disk? Is there any possibility to see the stellar wind or to detect stellar wind?
Yes, depends on the specific star, because there are interacting binaries where we also calculated some models. But sometimes it's indirect, because you have a wind model, and you have a wind, and this wind, the mass loss rate of the wind, the amount of mass, determines, for example, the X-ray emission of the secondary, if it is interacting binary.
Okay.
So the more mass goes, there is higher X-ray emission, and backwards, the X-ray emission influences the stellar wind. So it's kind of self-controlling engine. So this.
Yeah. Okay.
Okay. Thank you.
Okay.
We have to move to the next.
Yeah. Okay. Thank you.
Next talk. Olivera Latkovic will present us the joint work with Attila Cecchi. So I invite Olivera to share the presentation. Olivera Latkovic and Attila Cecchi are assistant researchers at the Astronomical Observatory Belgrade, and their research focuses on close binary stars.
Thank you, Olga. Can you hear me?
Yes.
Oh, thank you. I would also like to thank the organizers for the opportunity to give this talk, and also to all the participants in attendance for their time and attention. I gave a similar talk to this last year at the meeting Artificial Intelligence in Astronomy that was organized by ESO in Garching. There I showed some preliminary results of our first forays into applications of computer vision in the studies of binary stars. We have learned a lot since then, but this research is still a work in progress. I'll start with an intro to modeling of eclipsing binaries because, as Olga said, that is our main field of study. Specifically, contact binaries have some properties that make them especially attractive for automated analysis and applications of machine learning. Our ambition is to use machine learning as a part of a completely automated pipeline for modeling the light curves of contact binaries. And as a first step in that direction, we tackled the problem of automated selection of totally eclipsing stars using computer vision. Computer vision is a subfield of machine learning that deals with the detection and recognition or classification of objects from images. I'll tell you about the image recognition models we trained with synthetic light curves, how they perform compared to humans, and how they fared when applied to real-life observations. Eclipsing binaries are usually close and often interacting binary stars with nearly edge-on orbits, so that the components periodically eclipse each other. Although well studied, eclipsing binaries are still at the forefront of astrophysics because they allow us to determine the masses, sizes, and temperatures of stars with good accuracy, yet based on relatively simple physics. These stellar parameters are traditionally found by light curve modeling. Light curve modeling involves fitting synthetic light curves generated from a mathematical model to the observations. In this close-up, we can see a typical example. The observations are plotted as points, and the solid line is the synthetic light curve model, the synthetic light curve generated by the best fitting model to these observations. The model is parameterized directly by orbital parameters of the system and stellar parameters of the components. Finding those parameters accurately from a model is possible because they are encoded in the shape of the light curve. For example, the widths and relative depths of eclipses are indicative of the temperatures and sizes of the components, and the overall amplitude of the light curve is related to the orbital inclination. In detached binaries such as this, where the stars are spherical in shape, the light curve is mostly flat outside the eclipses, with bumps like these coming from mutual irradiation, and any asymmetries in the light curve are modeled with dark or bright spots. In semi-detached binaries, one component fills its limiting Roche lobe nearly or completely, and it is markedly non-spherical. This causes continual changes in the brightness, even outside the eclipses. Finally, in contact binaries, both stars exactly fill or overfill their limiting Roche lobes and share a common envelopy. Their light curves are characterized by continuous brightness changes and no clear transitions between the eclipse and out of eclipse phases. Now, the common envelopy of contact binaries is what makes them so interesting. This is because, in principle, it allows the measurement of a key parameter, the mass ratio of the components, from photometry alone. In most other cases, for a complete characterization of a binary system, the light curve isn't enough. It is also necessary to do time series spectroscopy and construct radial velocity curves. Radial velocities can then be fitted with a simple Keplerian two-body model to determine the mass ratio, which is equal to the amplitude ratio of the component's radial velocity curves. The mass ratio is needed to determine stellar masses and sizes in absolute units. Now, this is a problem with binaries from massive survey datasets because time series spectroscopy, especially of faint objects such as Kepler targets, is not easy to come by. But with contact binaries, we can skip this step. Because of the shared envelopy, the mass ratio is proportional to the size ratio. The mass and size ratios of contact binaries fall in this narrow strip limited by the inner and the outer critical Roche lobes. Since the size ratio is readily obtained from light curve modeling, the mass ratio can be determined without the need for spectroscopic measurements. However, it is only possible to get a reliable photometric mass ratio if the system is totally eclipsing. Otherwise, the size ratio and the orbital inclination influence the light curve in the same way, which leads to ambiguous solutions. The total eclipse provides a direct measure of the size ratio, constrains the orbital inclination, and guarantees the uniqueness of the best fitting model. And this is why total eclipses are important. Here are some nice examples of total or partial eclipses in contact binaries from the Kepler catalog of binary stars. A total eclipse, seen here, is recognizable as this flat region on the light curve, during which one star is completely hidden, and we only see the rear end of the other star, so the brightness is more or less constant. With partial eclipses, the brightness changes continually throughout the minimum, because we always see parts of both stars. Here are some not so nice examples from the All Sky Automated Survey, where the noise makes it harder to tell if one of the eclipses is total or not. Now, in case you wonder why we want to automate a seemingly trivial task like this, take a look at these numbers here. From a couple hundred contact binaries in the Kepler catalog, we have arrived in less than 10 years to tens of thousands in the Assassin archives, and more is coming in future surveys, much more. Another question that we faced when we started with this research was this: is the task of recognizing total eclipses really as trivial as it seems? The answer is unsurprisingly no. To my knowledge, human ability to recognize total eclipses has never been questioned really or measured in a systematic way prior to this work. In an experiment that I'll tell you about later, we found that noise makes this task quite difficult even for humans. But now we ask, how hard is it for computer vision, for a computer? And to answer, we train a series of image recognition models based on convolutional neural networks using TensorFlow for GPU. And in what follows, I will elaborate on their architecture, the simulated light curves that we use to train them, and how we evaluate their performance in the end on both simulated and real-life observations. Now, a bit about computer vision. Most computer vision methods are based on these convolutional neural networks, or CNNs. Like other supervised machine learning algorithms, CNNs learn by processing large numbers of labeled examples. In this case, those would be the images of light curves with either partial or total eclipses. Unlike most other machine learning algorithms, CNNs don't need pre-calculated features to help them discriminate between objects and images. They figure this out on their own by finding statistical patterns in the training data. Now, images are inherently more complex than one-dimensional data, so training CNNs involves more computation and requires larger numbers of examples than some other machine learning techniques. Training all our CNNs takes about a week on a powerful personal computer, but the application of a trained CNN, so generating the prediction of totality for a single light curve image, is near instantaneous. So here are some of these models. The simplest one, titled CNN3, according to the number of convolutional layers, processes input images of 32 by 32 pixels, these small images such as this that show only a single eclipse. A slightly more complex model with 4 convolutions is trained to process single eclipses in a bit larger images. A model with 5 convolutions does the same with even larger images of entire light curves. And the most complex model with 6 convolutional layers is trained with the largest images of whole light curves. Let's take a closer look at these various training examples. The computer vision models are trained with synthetic light curves, created using the same binary star model that I mentioned in the beginning. Labels for the generated images, so whether the eclipse is total or not, are assigned automatically based on the light contribution of the eclipse star. The orbital and stellar parameters of these light curves are drawn randomly from observed distributions. These distributions are the subject of the talk Attila will give tomorrow, so I'll just skip forward to the treatment of noise. As we will see, noise has turned out to be a key factor in the success with recognition of total eclipses. So we generate training images with 3 levels of noise. First, with no noise at all, like in these examples here. These are the generated light curves, and the binned light curves from Kepler look about the same. Then we have light curves with moderate noise. Such noise is occasionally also present in binned light curves, and it is roughly representative of what we would expect from ground-based observations of individual objects. This number, 0.02, this is the standard deviation of the normal distribution that we draw the noise from, and it is relative to the amplitude of the light curve. Finally, the high noise examples are similar. So here are the generated examples, and they're similar to what we have seen in the light curves from ASAS. Both the simulated training data and the observations we later use for evaluation are processed according to the script outlined here. First, we make sure that both eclipses are always visible. We stretch the light curve along the vertical axis to fill the height of the image completely. We shift the phases so that the deeper minimum is always placed on the left side of the image. We bin the light curve so that every point is represented by exactly 1 pixel. And we finally cut out the eclipses for the models that work with eclipse cutouts. To validate computer vision performance, we again use simulated data and test the system on labeled light curves that were not used for training. But we also test it on real observations classified by humans. Now here we touch on a problem I hinted at before, the reliability of human performance. With generated data, we have access to ground truth. But even synthetic total eclipses can be made to look like partial ones if there's a lot of noise or if there are too few points in the eclipse to make out its shape. Noisy and marginal cases are a problem both for human and for machine classifiers. So to measure this, we did tests with synthetic data for which we could later look up the ground truth. This was done last year, so these images differ a little from what I've been showing you so far. The two of us, Attila and I, looked at sets of 500 generated images in each of these two image sizes and with all three noise levels. We got, on average, 97% balanced accuracy on noiseless examples, down to 85% accuracy on noisy examples, which means that in the presence of noise, we misclassified 15% of the light curves. Let us see how this compares to computer vision. When evaluated with test data generated the same way as training data, our image recognition algorithm works great. These colors here, they represent different noise levels. And the performance obviously declines as the noise increases. And the different line types, they represent the images of different sizes. And increasing the image size improves performance, but not as much as we initially expected. Finally, from left to right is the size of the training set, starting from 500 and ending at 75,000 training examples. And every time they are divided equally between the two classes. Now, these thick black lines show the human performance levels we've seen in numbers on the previous slide. So this tells us that computer vision can surpass humans with this task, at least with synthetic light curves. Here is the same plot, but when the models are evaluated using Kepler data instead. The results are still good, but not as good. The best models trained with moderate noise reach just above 90% balanced accuracy and surpass human performance on noisy light curves. We can see that the models trained on noisy data perform very poorly here. This is expected because the training light curves generated with high noise look nothing like smooth Kepler observations. This performance metric, balanced accuracy, is used instead of the ordinary accuracy, and that would be the ratio of correct classifications to the sample size, because observational data sets are imbalanced. That is, there are far more light curves with partial than with total eclipses. And in the case of the Kepler catalog, the imbalance is quite severe. Out of about 300 contact binary light curves, only about 30 or 10% show total eclipses.
You have 1 minute.
Thank you. Balanced accuracy is the average of the so-called true positive rate and the true negative rate, and it's used to offset the class imbalance. Like I said, these results are good, but we'd like them to be even better. What we would like is to achieve the level of performance we've seen with the generated test data. I'm going to skip these next few slides and just jump on to the summary. In summary, contact binaries are a treasure trove buried in underutilized survey datasets, and one of the first steps in utilizing them is finding those that display total eclipses. A computer can be trained to do this by looking at the images of light curves, and in theory, it does even better than humans. The models we trained on generated data aren't quite there yet, but we are still tweaking them and hope for the best. That's it. Thank you.
Thank you very much, Olivera. Do we have questions for Olivera and Attila? I don't see hands raised. No? Please use also chats for comments and questions. So if we have no question, we shall go to have a break, afternoon break or midnight break. And we continue the conference at 4:15 Belgrade time or 1:15 Melbourne time. Okay, thank you very much.